So, but you need to know it just in case one comes up. They're rectangles. All right, so relative frequency histograms that are symmetrical and bell-shaped are said to have the shape of a normal curve. You already know that. Here's a normal curve. If a continuous random variable is normally distributed or it has a normal probability distribution, then a relative frequency histogram of the random variable has the shape of the bell curve, and it is symmetrical. We've dealt with this a lot, so you already know what this stuff is. Quick reminder, this place right here, where we mark our first standard deviation, is the inflection point. That is the place where the curve goes from being concave up to being concave down. There's an exact place where you're like, I'm going up, I'm going down. So that place is your inflection point, and that is where your first standard deviation occurs. Here's a couple of other examples of normal curves. Normal curves don't always look the same, depending on what your mean is or what your standard deviation is, but they are always symmetrical. And always, how much data is inside the first standard deviation of a standard bell curve? 68%. And inside of the second standard deviation? 95.
95.
Inside of the third?
98.7.
Y'all are so short. So, here we go. Properties of the normal density curve. This is all stuff you've learned before, so none of this is new. It is symmetrical about the mean, mu. Because mean equals median equals mode, the curve has a single peak, and the highest point occurs at x equals the mean. It has inflection points at the mean minus the standard deviation, the mean plus one standard deviation. The area under the curve is 1. The area under the curve to the right of the mean equals the area under the curve to the left of the mean, and they are both half, 50%. Because if you folded it in half, remember it has total 1, so half's on the right and half's on the left. As x increases without bound, getting larger and larger and larger, the graph approaches but never reaches the horizontal axis. And same thing is true on the left-hand side. As it decreases without bounds, it gets more and more and more negative. The graph approaches but never reaches the horizontal axis. Then there is your empirical rule. Approximately 68% of the area under the normal curve is between the first standard deviation, 95 is under the second standard deviation, and 99.7 of the area is under the third standard deviation, and then the 0.3 is the fact that it's asymptotal, and it's not actually getting photographed. So there's the picture again. Kind of hard to read those 34s, but I think we know that now that we've been reminded. All right, 2 separate ways to interpret the area under the curve. Suppose that a random variable x is normally distributed with a mean mu and a standard deviation of sigma. The area under the normal curve for any interval of values of the random variable x represents either the proportion of the population with the characteristic described by the interval values, or the probability that a randomly selected individual from the population will have the characteristic described by the interval values. It's proportion and it's probability. That's what that number represents. You can turn them into percents if you want to. You can leave them as decimals. I've noticed on my labs that when they say probability, they usually mean the decimal. If they want the percentage, they'll tell you they want the percentage. But either way, it's a proportion, it's a probability, it's a percent, it's all those things. So let's do one, because I think that they make sense. Wonder why I didn't put a curve on this one. Dang it! I skipped it, I guess. I don't know. The weights of giraffes are approximately normally distributed with the mean of, the mu is 2,200 pounds, and a standard deviation of sigma, 200 pounds. Draw a normal curve. Okay, there we go.
This is the best curve I've ever... Oh, wait. Is this supposed to take up the whole page?
No, I didn't have to. Oh, mine didn't. You can, that's fine.
Mine's a good curve.
That's pretty good.
Not erasing it.
Draw a normal curve. Shade the area under the curve to the left of x equals 2,100 pounds. Okay, I'm going to mark all my stuff first. So my mean is 2,200 pounds. My first standard deviation. How did I get an extra 0? Oh, sometimes I make myself crazy.
You make me crazy too.
Oh, sound like my kids. They say that too. They're like, Mom, seriously. Oh, now I made this come out too far. Oh my gosh.
Just scribble out the last zero.
I'm having a trauma today. Okay. Well, now you can kind of see it. That's okay.
Yeah, I'm having trauma too.
2,400. This is 2,000. And this is 1,800. That's terrible. Oh, wow. Okay. That's terrible. Sorry. Okay. Shade the area under the normal curve to the left of 2,100. So that would be right here. Shade to the left. Suppose that the area under the normal curve to the left of 2,100 pounds is 0.3085. Provide two interpretations of this result. Well, that would be 0.3085 the probability that a giraffe weighs less than 2,100 pounds is 0.3085. That's one way to look at it. Or I could also say 30.9% of the giraffe population weighs less than 2,100 pounds. Or you could say, I put it as a percent, but you could say the proportion of giraffes that weigh under 2,100 pounds is 0.3085. Everybody okay? Does that make sense?
No.
No?
Yes, but
Once again, I
wondered.
did a bell curve, I was trying to put all the numbers on, and I looked up and the whole problem was solved.
Yes.
I didn't have to solve. You didn't solve anything. You just shaded. There's nothing to it.
So the 0.03
They gave it to you.
0.30. Oh, okay. Okay.
I mean, literally, you didn't solve anything. You shaded. That's it.
Cool.
And interpreted, but they gave you the interpretations. But
Yeah, I just realized that.
Yeah, I have
I
like.
shouldn't have even like worked it down. Because I wrote it so mentally.
no, I didn't do it good either. So, all right, standardizing. Here's our favorite formula. Yay!